welcome back to the tech track. Now it's a lot easier to think with something in your belly, I think. So I'm going to talk about a few trends that we see in the industry recently, because there's a lot of change, and there are a few concepts that keep popping up, and the technology landscape is really, really changing. The previous speakers have been talking about the data lake, of course, but also about microservices, about real-time infrastructures, the fact that big data is moving away from like batch processing towards a more reactive style. So it's getting closer to the mainstream, if you like, in the way it's architected. So there's a lot of blending happening between the mainstream technologies and big data specific technologies, and there's a lot of transformation in the big data field because we're moving away from a, if you like, a more scientific field towards a more engineering centric field, right? So now we deal with a lot more challenges around availability of the systems as well as reaction time. So my talk is going to be about this blending of, if you like, operations and big data. And as Joanna was saying, essentially, I'm a developer. I've been a developer all my life, although right now I'm in the role of a product manager for Bigstep, and I'm helping them build products and services for the big data market. And I'm going to talk more about Bigstep at the end of the presentation if we have time, but if not, we can always talk about it at our booth. And yes, I'm a bit passionate about distributed computing. You could say the least. So as I was saying, there's a lot of blending between these two worlds, right? So we see microservices in big data. We see microservices running Kafka, for instance. And again, I'm going to talk about what microservices mean. And we see big data technologies being used in the mainstream, right? So again, we see Zookeeper being used in web-based applications to synchronize multiple applications, or Kafka being used in web-based applications, or just the approach in general being used in regular back-end systems for websites, right? Distributed systems, NoSQL databases, everything is popping up all over the place. So big data as a concept, I think, tends to disappear in favor of normal data, right? So in the end, we all gonna have to deal with what we call today big data. So it's gonna be normal data, normal business as usual for IOPS and IT in general. So we might as well accept it that everything is blended up. Yes. So the concept of a data lake, for those of you who are not yet familiar with it, is the idea that, of course, you have to accumulate a lot of information because it might prove valuable at a later point in time. And maybe in the same way a mummy gets more interesting as you throw new technologies at it, such as X-rays, you find new information from the same artifacts, right? So on the same logic, keeping your data for a longer period of time makes a lot of sense. Now, there's a lot of problems that derive from this simple vision because you can't simply throw in data in a data reservoir or data lake and expect that somebody's going to make sense of it later on. But again, we're going to talk about it. The concept is essentially it's not about the technology itself, but it's rather about how you use the data lake inside your organization. And the scope and the purpose of a data lake is to promote essentially innovation. Because if you allow your IT organization to leverage freely available data and freely available processes and domain knowledge, then you can promote smart people to do small things with data, things that maybe the business people have not thought about it, or even accelerate the innovation process by simply having access to data. And again, I'm going to talk a bit more later on. And of course, it's important to keep data in its original format, but it's not the format that's important, but rather the information that's stored alongside this format. So the format itself is data as well, is information. Okay, so again, the data lake is not a giant universal database. So Bigstep has been doing work with the TFL. I think Charles mentioned it. This is how the TFL dataset looked like. And my point here being that without domain-specific knowledge, it is virtually impossible to make sense of data in general as it is stored. This particular dataset shows, because the TFL has sensors on a road, and between two sensors, a car can pass or a bus can pass, and then this is a recording of those events if a car is on a sensor or it's not on a sensor. So it's a lot of information in there, right? Really valuable information about how traffic moves and how traffic flows within London, but making sense of it requires a lot of domain knowledge. So what do you do if after 10 years, you don't know what that means anymore? So the data will become essentially useless. So what my point is, it's a bit more complicated. And so to be able to make sense of the data, you need, as I said, domain knowledge, you need clean data. Somebody was saying that about 50% of the data scientists' time is spent on cleaning data, right? So you need to be able to clean data or at least have cleaned data. You need to have documentation, data documentation. So what is that thing, in the end? And you want to have ETL processes to move data from the production systems into your so-called data lake or data pond. And also, importantly, information is not just in the data. It's also in the code, in algorithms, and processes, perhaps. So associate algorithms associated with particular sets, but sets of data is also something that needs to be stored on the long term. And HDFS, again, is just a storage medium. It's just a small part of the equation. It's not the fundamental thing. And that's why I'm going to talk about microservices and how to create a proper data lake that serves the purpose that the data lake is trying to achieve, but perhaps doing it in a smarter way. And my view is that a proper data lake is a data lake that's actually a collection of data services. And a data service is essentially a service that provides data to all the other services within a company. And it not only provides real-time information, but can also provide a structure to unstructured data. It can provide a schema for schemaless information. It provides also documentation, because an API is also, for coders looking at the properly designed API, that's also information about how to connect things together. It also allows you to write code that cleans the data, imports the data, but that's agnostic to what's underneath. So it facilitates connections between data to facilitate, again, references and cross-checks and cross-references between data sources, because that's where the most value is at. And I know this doesn't make a lot of sense right now. We're going to see later on what I mean by that. But essentially, we see services that don't have any data stored behind it. We see services that just store data. We see services that rely on others, and it's a more complicated view, but you'll see it's starting to become simple. So an example of another project that we worked on for a big logistic company in the UK, what we did was we analyzed the driver's journey. Essentially, a driver picks up a parcel at one point and delivers it at another point, right, across the UK. And during the journey, they have this mobile device that they use, and that tells us where they are at that particular moment and where they picked up that particular parcel and where that was dropped off. So we had this information. The service within our data lake is called the driver service. This handles and provides information about the driver's journey to the rest of your organization. Then we have another service for pickup and drop-off that analyzes pickup and drop-off points, and can be used to do a little bit of k-means or clustering analysis to see where the highest concentration of pickups and drop-offs are. So that's another service, independent from the driver service, by the way. For each individual, let's say, cluster of locations where a pickup appears. Another service deals with the timetables, or the probability timetable, if you like, of a particular parcel being, let's say, created in a particular location at a particular time of day. So we can say that, somewhere in Manchester, at 9 a.m. in the morning on Fridays, a lot of parcels are coming in. So we can do predictive analytics, and we can predict that the driver has to be somewhere nearby. Right? So this is the job of the cluster service. Then we have another service called the route service that knows about routes. Right? So all these services are independent from each other, and any one of you can use it at any point in time to essentially improve the company's performance. And for instance, what the driver service can do is to use TfL traffic data as well as cluster timetables to send instructions to a mobile device, so the driver's mobile device, so that the driver knows where to be at one particular point in time and which route to take to its destination because of the likelihood of picking a parcel along the way. Also, of course, we can record a lot of historical information. So all these services are interconnected. Now, microservices in general are not about the technology either. So they are based on, they've been essentially evolving from the realization that team dynamics is one of the biggest problems in developing software nowadays. And this guy, Conway, postulated that the communication patterns within a team, essentially, will be translated directly into the communication patterns and the architecture of a distributed system. And what that means is that if you have a very simple, let's say this very abstract, simple team organization where you have like data modeling guys, back-end developers, and then front-end developers, whenever you want to build a big application, you have to wait until the models are properly designed, you have to wait until the backend is properly implemented, and then at the end start working on the UI. You can't do it all at the same time, so it takes X months, let's say. Whereas in a microservices environment, the purpose is that you might want to have individual teams specialized on each individual microservice that just does a single job, like a shopping cart in a big website, could be a service in its own, could have, most importantly, a release cycle of its own. Right? So having a release cycle on its own means that that team, that small team that might have a model specialist, back-end specialist, and a front-end specialist, could develop its little piece in isolation from all the others. And so a big project split into multiple teams could be developed in parallel. So if you like, it's a distributed processing applied to teams. And to make that, of course, this is pretty simple. We haven't applied this model until now because of the problems that arise was that the connection between multiple services across HTTP was incurring. So there's a lot of latency that was traditionally associated with having many components talking to each other. But nowadays, we have a few technologies that helps us do this properly in production. And so we can leverage them to actually achieve this thing. Derived from the fact that you have multiple teams is also the idea that you might have a multitude of technologies being used underneath, right? So perhaps for the shopping cart, it's a lot, because it's a UI-heavy component, you might want to have some dynamic templating system being used, and then some very fast NoSQL database to serve what's in there. So you have polyglossy, if you like. We have multiple languages being used in different technologies, but at the same time, what you have is in different storage technologies, so different persistence layers for each individual component. So as opposed to having a single database with this, and scaled by having all application servers connect to that database, which could scale or not, You instead have independent storage layers, and the microservices talk to each other rather than connecting directly to the underlying database. It's a much, much easier way of building an application that's better for resiliency, for the time it takes to actually develop those components, and as well as performance in general. Right, so one of the things that you want to use in building microservices for a traditional infrastructure or data services in a data lake is Docker. You've been hearing a lot about it recently. It's because it's really, really high performance. It's a high performance technology because it does not have a hypervisor per se. It does not essentially simulate hardware onto which each individual machine has a kernel. It uses the same kernel and individual processes within it. I can get into more details, but the idea is that virtual machines or Docker containers are identical to processes in a Linux environment, apart from the fact that they're really, really well isolated between themselves. So it's a very good technology, especially on bare metal machines and bare metal cloud providers, because you get really low latency. So which is a key factor for microservices, because as you've seen there, real-time reaction is paramount, and so being able to react in nanosecond or millisecond really helps. And so avoiding virtualization helps you get this reaction time up and running really fast. Again, I can get into a lot more details about it. It's not necessarily about the containers themselves. Docker containers as a technology have been around for a while. But Docker also introduces a concept of infrastructure as code. So instead of mingling with the operating system, like doing upgrades of an operating system, using Puppet or Chef to deploy stuff on an operating system, what you do instead is the developer develops a Docker image, pushes it within his own development environment on his laptop, then pushes it to a repository of Docker Hub, where Jenkins or another continuous integration environment can take it and deploy it in a testing environment, and then subsequently into a production environment. So what's important about Docker, what's new about Docker, and it's brilliant, is this infrastructure as code component, because sysadmins are very rare nowadays. Developers tend to do everything on their own, and so this is a lot better for developers than managing operating systems. Also, whenever you want to do an upgrade, you just kill a container and put the newer upgraded version instead of doing upgrade like dist upgrade on an operating system. That's really, really important. Really important. So if you don't have to manage operating systems, a whole lot of complexity goes away. Performance. This is a benchmark that I did at one point at Cassandra for Cassandra, and this is about latency. As you can see, there is a little bit of an impact, which stems from the file system that Docker uses rather than everything else. They use something called UnionFS, which I'm not going to talk about right now. But the idea is that this is milliseconds, right? So 90 milliseconds versus 21 milliseconds in response time for a particular application, which is really good. I mean, it's really fast. Throughput as well. Really fast. Now, problem with building a data lake using Docker containers is that Docker itself does not know about multiple servers, at least not right now. They're working on it. They have a few services around orchestrating multiple Docker containers, but the problem is that you don't want to, again, access it to each individual host and create Docker containers on it. You would much rather just submit an API call and have a Docker-based application that has multiple containers spun off across a big cluster of components. It's something that we are in big data been used for in dealing with Yarn, for instance, right? So, and this is where Mesos comes into play. You've seen Charles talking about it as well. So Mesos is another resource manager that, coupled with Marathon, that does the actual spawning of Docker containers, creates this platform as a service environment that exposes an API that you can use to spawn these containers. And it supervises the containers. If one dies, it will get restarted. It manages HA proxy configuration, which does load balancing automatically. And it asks Mesos for resources, right? Very, very Good. And also, this is something that you can install on any cloud provider. So it's your own personal platform as a service thing. Now, about streaming in general, you've been hearing a lot about moving away from batch processing towards streaming. Well, this is another. The problem is that with batch processing, you had the usage pattern that's essentially 100% utilization for a period of time, then you do nothing. Then another 100% utilization for a period of time, then you stop, which is good, but you had to have those servers up and running for that period of time. It's pretty simple. But with real-time information, with real-time reaction, what happens is that the usage pattern of the computational resources resembles what we see in web-based applications, right? So it's something that's seasonal. It's something that varies with the user interaction, right? It follows the day and night patterns. And so you need consolidation. You need to be able to use that extra capacity in a way that's efficient, right? So you can't just have servers waiting around for traffic to come in, because that's not cost effective, even on a cloud provider environment. So what you want to have is you want to have the ability to flexibly move computational around across servers, so that when systems are not used, you squeeze all your services within a particular set of physical instances, and then you scale out and then you scale back. So streaming, Spark streaming and big data starts to be a lot like your regular website. By the way, you can use Spark with Mesos directly. So the same cluster, the same Mesos cluster that can run part of your application stack and part of your data services can actually run as a resource manager for Spark. So you can submit jobs to it directly, and it will spawn Mesos executors in either coarse grain or a fine grain way. So it's very interesting. So I know I've been running, very fast on these technologies, and I can get into a lot more details if you like. How much time do we have left?
About
5 minutes. Okay. So it is, as I said, important to build data services, right? And you have technologies to do that nowadays. And a data lake is a collection of data services. And to be able to build this data service, there's another set of technologies that you might want to look into it, and that's microservices frameworks. I think Neil spoke about Vertex.io. There's another one which I've used, which I like. It's called Qubit. There's another one called AKKA. And these frameworks are like Ruby on Rails, but for microservices. If you've ever used Ruby on Rails or J2EE, or frameworks that allows you to create microservices. They're very, very small. Very fast. They expose either REST interfaces or WebSockets interfaces to your data services. And so whoever wants to build something new, think in terms of Google, right? Google has this 20% of the time available to do whatever you want. Try to apply that idea to an organization like a bank that has a data lake that's open, that describes things, and that provides these data services as APIs. This will mean that some smart guys could actually build new and interesting services without having to have real deep access to the ETL jobs, to the structure of the data, to everything else. Of course, there are a lot of problems with microservices, things that get, if you like, in the way sometimes, which is, schema evolution. So if you have multiple services communicating with each other at the same time, chances are at one point you'll do a release, and so you might break compatibility between two different services. And so, but there are solutions to that problem, which is, for instance, the schema repository of Kafka. And so there are ways of mitigating it. So I can get into a lot more details, but we can take that offline. Also about Bigstep, stop by our booth, and we'll talk a bit about how to build data lakes on a bare metal infrastructure. And we're really, really fast. That's the key component. No, I'm not joking. So really fast. That's why a lot of our partners are using us for demos, essentially. I mean the partners that you see down there. So that was my talk. I hope you liked it. We have a lot of. If you have questions, just shoot an email over, or again, stop by our booth and ask us. Thanks. Thank you.
Thank you. Questions? Okay, let's start over there.
For a business that doesn't have a data lake at the moment, but would like one, where do we start, and particularly starting small?
So I would think in terms of what you want to accomplish with that and how your data looks like, first of all. There are a lot of solutions of doing it simple. So the easiest thing that you can do, of course, is try to accumulate data in something like HDFS. But as I said, you have all these problems. So what I would do is I would kind of try to put a team together. So as I was saying, team dynamics is really the most important thing. So put a team together that has this cross-functional description, if you like. So you have people that know about the data, people that know about domain-specific knowledge, like what does that data actually mean. Also some hardcore programmer together in a room, and have them build a service, one service for starters. See what happens.
We had a second one over there.
I was just wondering if you could elaborate on the kind of the data team idea that you were talking about, trying to break the barriers between, say, 3 different sets of team, like your database people, your modelers, your back end, your front end. What in your head, what would a solution kind of look like?
So yeah, very good question. I have that question asked last night as well at Hadoop Users Group. And how do you do agile with this thing? Because this makes sense, but how do you stick it into an agile environment? And the answer is I don't know. But I think that it really follows the agile manifesto.
Alex, I told him you know everything.
But I think this follows truly the Agile Manifesto and the idea that if you want to be truly, flexible, if you distribute workloads in this way, you can have like little Scrum teams, right? Each individual team is a small team. So having a small team is really important because the communication complexity that grows exponentially with the number of people in a team. Right? So if you have small teams, communication is really fast. So that team is a lot more agile than the entire big Scrum team. Right? So I would say that you will need a bit of a process change probably, but if you can do it, it will be brilliant. Or at least that's what I think. Did I answer your question? Okay. All right.
Okay, thank you.
Thanks.